So YouTube is not working.
I think now it's moving to it. It was not working the last talk, but let's see. Let's cross. It's working now. It's working. We are back.
Now we have Isaiah.
Yeah, we have the recording. Yeah. So
Yeah.
we put there.
Yeah, we needed this kind of bump to be more feeling at Rio. If everything works smoothly, we feel like we are in any place, but we are not. Now, right now, we are in Rio, so it's more real. So we are. I'm ready when you want, Alexander. And
Right. Yeah.
Okay, then. So, so it's a pleasure to me to introduce the next speaker, which is Daniel Ismanuel from ICMC and from São Paulo. And well, Ismanuel did his PhD at IMPA, and so and visit UFRJ many times, and also Rio for many other reasons, and so and it's quite active in mathematics in Brazil, so and the rest of the world. So it's a pleasure, and he will talk about transfer operators, atomic decompositions, and Bezoar space. So
Thank you very much, Alexander, for the presentation. By the way, this is a joint work with Alexander. So it's always good to have the chair has the collaborator, right? And okay, so for me, it's I'm very happy to participate in this celebration on the 50th year of the graduate studies in Federal University of Rio de Janeiro. I visit Federal University of Rio de Janeiro many times. This is a picture of one of the trees in the campus. It's Abricó de Macaco. I discovered that later, and it's from Amazon. It's actually a very beautiful campus. I like a lot of trees and exotic trees like this one. Okay, so I'm going to talk about transfer operators, atomic decomposition, and Bezoar spaces. I think my internet is okay, but if you have some difficulties to something, let me know. Okay, so I'm going to talk about works that was in a lot for preprints actually. The main one is transfer operator atomic deposition with Alexander, and the other ones that you see listed here. Okay, so let's start with the problem. What I wanted to do is study ergodic theory of expanding maps. Okay, not necessarily Markovian expanding map or C2 Markovian expanding map like this one, but Markovian expanding maps in a very general sense. Okay, so let's start with this one that is a very classical situation. Pick, for instance, expanding map in the circle. That's C2. So this is a Markovian map like this one. And we know, maybe in your first course of ergodic theory, we learned that this has a unique invariant probability that's absolute continuous with respect to Lebesgue measure. And this one is the unique physical measure of these dynamical systems. And what is nice about these dynamical systems, this kind of dynamical system, expanding maps, is that this measure, the ergodic theory of these maps, is very rich. You have a lot of nice properties for this invariant measure. For instance, if you have an observable that's regular enough, let's say Holder, then you have exponential decay correlations for this. You have uniqueness of the absolute continuous invariant probability. For Holder observables, they satisfy central limit theorem. And you have also other technical but quite useful properties like analysis of the topological pressure for Holder observables, for instance. So they are it's a very rich theory. Okay, and turns out there are many ways to prove these properties. Actually, it depends what you like. Some people like probability couplings. Other people like work with the environment measure itself. I like, and many people like, using study these properties using an object that's called the Perron-Frobenius, Huel-Perron-Frobenius operator. And what is nice about this is that just only study this object, just this object, you are able to get all these properties. So that's a very practical way to study ergodic theory of these maps. We studied just the spectral properties of the Perron-Frobenius operator and other kinds of properties of this operator, and we were able to prove all these properties. Okay, I'm not saying that these implications are easy. Some of them are easier than others. Some of them needs more additional properties of your map. But let's say that to study the Perron-Frobenius operator is probably the main difficulty to deal with this. Okay. Okay. So what's the Perron-Frobenius operator? So this dynamics has this property. If you pick a measure, absolute continuous invariant measure, absolute continuous measure, and push forward this measure by the dynamics, you get absolute continuous measure. So if you start with a density psi, and pick the push forward of this measure, you get another absolute continuous with some measure with some density. And this density is exactly the Perron-Frobenius operator applied to psi. So L gives you, that's a linear operator, actually a bounded linear operator in the space of densities. This is describes the action of your dynamics on the measures, on the absolute continuous measures, okay? So that's why they are so useful to study ergodic theory. And okay, so if you have a countable number of branches, this is pretty much the formula of the Perron-Frobenius operator, okay? Okay, that's it. So this we started studying Perron-Frobenius operators in the 50s with Richard. So he introduced the Perron-Frobenius operator, and he asked to study the existence of invariant measures for many-to-one transformations. This is his paper. It's a very short paper, maybe 15 pages, something like that. And this paper is not very popular, but a few years later, in '64, Ulan wrote a book on open problems in mathematics in many areas. And one of the chapters was about this Huel-Perron-Frobenius, but now call it Huel-Perron-Frobenius transformation, and ask if something similar to the Perron-Frobenius theorem for positive matrix holds for this operator. So you can see that this operator preserves positive functions. If you start with a psi that's positive, then the image is also positive, at least in this setting of shift operators. So it's analogous to a positive matrix, and Ulan asked if it's possible to prove something similar to the Perron-Frobenius theorem for positive matrix. And who gave an answer for that, a positive answer for that, was Well in the 60s, in the end of the 60s. And actually in the abstract settings of shift operators, of symbolic spaces. But at the same time, actually in the same year, Sinai published the construction of Markov partitions for some hyperbolic systems, like Anosov systems. So this allows you to use this abstract theory using symbolic dynamics for many dynamical systems, okay? And then you can construct the SBR measures for Anosov diffeomorphisms and so on and so forth. So there's these two results, the existence of Markov partition and this result of Borelli was a huge influence in ergodic theory of smooth dynamics. Okay. So what kind of property this operator should have to be able to prove this stuff about the cave correlations and things like that? So when you study this operator in the integrable functions, L1, you can see that this operator is bounded, is what you see here in the left, okay? But turns out that the spectrum of this operator in L1 is a full unit disk, is the full unit disk, is this blue ball that you see here. And that's very bad because most of these results that you see there, the cave correlations and um, uniqueness of the invariant probability, the central limit theorem, depends in the study of the eigenvalues of the performance operator. So the fact that the spectrum is the whole full ball, the essential spectrum coincides with the spectrum, put a lot of difficulties to understand this operator in L1. Okay, actually, if you pick an observable that's just integrable, usually this observable doesn't have satisfies exponential decay correlations, central limit theorem, and so on and so forth. Okay. On the other hand, there are operators that has a very good spectrum that are the compact operators. The compact operators, the spectrum is just a countable number of eigenvalues converging to zero. Okay, and so this is very similar to the finite dimensional situation. The finite, you pick a matrix, the spectrum is a finite number of eigenvalues, and it's pretty much the same for compact operators. But this situation, usually the performance operator is not compact operators, not compact operators. There are some situations, for instance, if you have a real analytic expanding map of the circle, where the operator is a compact operator, but usually it's not. So you cannot use this picture. This picture is very hard. So what happens is that usually what you prove is something that's a mixture of these two behaviors that you see here. You have the spectrum close to the unit circle is like in this case, you have just a discrete number of eigenvalues, okay? And when you're close to the zero, you have some weird stuff, but you don't care because most of those properties that I told you, like exponential decay correlations, depends only on the behavior of the spectrum close to the unit circle, okay? So this is called quasi-compactness, okay? So if you find a Banach space of functions where the performance operator behaves like a quasi-compact operator, then you can prove all these wonderful things, okay? Okay. So one example is the following. In this setting of expanding maps of the circle, you can pick the space of holder functions, okay? So in this space, the operator acts as a quasi-compact operator. You have this picture in the middle, and you can prove all that wonderful stuff, okay? Another way to see this, okay. Another way to see this is to okay, I forgot something. Okay, so the idea is the following. What you wanted to do is to have weaker assumptions about this expanding map. So expanding maps of the circle are very, oh no, you know a lot about this. It's like a toy model for more complicated situations. For instance, you can have no Markovian, you don't have a Markov partition that is invariant by the action of the map. You may have discontinuities. The derivative maybe is not holder, is not p-bounded variation. The phase space of your map is not simple like an interval. Maybe it's a fractal, Julia set or something. Or maybe you have infinite many inverse branches. So all these more weaker assumptions pose more difficulties to understand the ergodic theory of these maps. And another thing that you wanna is a large class of observables where you have exponential decay calculation, central limit theorem, and so on and so forth. So you cannot pick all the integrable functions because it's just not true that they have these properties. But you don't want to pick a very small set of observables because in applications, maybe you want to observables with discontinuities, unbounded observables. You want a class, a natural class of observables like Sobolev functions, where you wanted to apply these statistical results. So that's the goal. That's the goal, to find weaker assumptions of your expanding map, and at the same time obtain a large class of observables with these nice statistical properties. Okay. Okay, so there's a long story about this. I don't have enough time to talk about this. This started with Gauss, Borel, Henry, Ulan, well, of course, Sinai, Walters, Bowen. That's not here for some stupid reason. I don't know why I didn't put Bowen there. But for this method using quasi-compactness, it's relatively recent thing. Starting in the 70s with Lasota York and Keller and Hofbauer. And for each kind of dynamical systems, you pick a different space, okay? Because this space should be invariant by the action of the conformance operator. It should be quasi-compact action. So in Lasota York, he studies piecewise C2 expanding maps. And for this class of maps, they use bounded variation space of functions. Keller needs a larger space to study C1 plus alpha piecewise expanding maps on the interval. So using a similar space for multidimensional expanding maps. So there's a long story. I don't want to go. Let's just sit on another one. That's Tomini. They use Sobolev spaces. Liverani use a space with regular measures of certain kind. Islami uses something similar to standard pairs that Chernoff and Dogopia use it to study billiards. So there's a really long story about this kind of method. So what are the main results? So the main result is a little technical because I'm going to construct this family of functions where you can prove this quasi-compactness. So I'm not going to give the statements of the main results, but let me just tell you the following. We build a family of Banach spaces of functions, and to define these spaces where you're going to have these nice statistical properties, you just need a very mild structure. You don't need to be a manifold or interval or a hyperbolic Julia set. It just needs to be a measure space with a sequence of partitions, okay, as we're going to see. The second thing that's nice is that in many settings, this space coincides with Bezov spaces. That is a very popular space of functions, okay? What is nice is that you can also get explicit formula estimates for the essential spectral rates, that little blue ball that you see there in these pictures. You can apply this for all the expanding maps, piecewise expanding maps, and multidimensional expanding maps, and new kinds of expanding maps. And you have statistical properties for observables in the Bezov spaces. So this is really interesting. Okay, as I told you, I'm not going to give you the description of the main, the formal announcements of the main results, but let me give an example, a set of examples where you can apply this theory. I call it the bestiary, and there are many kinds of examples. So let's start with a very regular map. Pick, like, say, a very regular map and F1. So you have a piecewise affine expanding map, and you perturb a little bit by something where the derivative is very regular that belongs with this Bezov space here. So if this perturbation is very small, then you can apply this theory and prove that the performance operator is quasi-compact in this setting. Okay, so to have an idea how bad this derivative can be, for instance, if you pick this derivative has this behavior, it oscillates infinitely, very fast, converging to some point, then you can see that this function cannot be Holder, cannot be bounded variation, cannot be p-bounded variation. So it's more general than the usual set of potentials that you can you do thermodynamical formalism. Okay. What more can you say about this? Another class of examples where you can prove this nice results is that ergodic results about these maps. You pick a piecewise expanding B-Lipschitz map where the derivative has 1 over beta bounded variation. So Keller studied these kinds of maps, and he constructed by hand some Banach space of functions where you can prove this Lazotta-York this quasi-compactness. Okay, but here you can actually use a classical Bezoff space in the real line and prove all these nice results about the ergodic theory of this. One of them that I found very interesting, people usually don't pay too much attention for this, is that one that I emphasize in orange. So this is saying that the invariant density of the invariant measure, absolute continuous invariant measure, is the support of this is an open set with up to a subset of a zero-Lebesgue measure. So you can say something about the support of the measure, what usually is very difficult if the potential is not very regular. Okay, so if your potential is like Holder, log of the derivative is Holder or maybe bounded variation, then okay, you can usually prove this kind of statement. But if the derivative is not very regular, then things became more complicated, and you can prove something like this using this setting. Another situation that you can do this is piecewise expanding C1 plus beta diffeomorphisms, like this. Okay, and in this case in particular, you can give a very nice expression about this essential spectral radius. Again, this space is the classical Bezoff space. Okay, Lorentz maps, the same thing. So for Lorentz maps are maps where the derivative explodes when you approach some point in a certain way. So in this setting, you can also prove all the nice ergodic, have all nice, very nice ergodic properties. Okay. For Markovian expanding maps, you can actually, in this case, is an abstract theorem. So you have a metric space that's alpha is regular, and you have a Markovian map in this metric space. So you can define the Panford-Benz operator with some potential, and you can give estimations for the essential spectrum radius in this abstract setting. Okay, exactly. So, but in this case, because it's a metric space, typically this space is not the classical Bezoff space. It's something similar, but it's not a classical Bezoff space. Piecewise expanding maps in 2 or more dimensions. If you have some, so in this case, usually you need some additional information about the map to include the existence of absolute continuous invariant measure. So under certain conditions, that is necessary actually in these settings, there are examples of piecewise expanding maps in R2 that does not have absolute continuous invariant measures, but under certain conditions, you can use this theory to study the ergodic theory of these maps. Piecewise expanding maps in RD. So you can also prove all these nice results in this setting. Julia sets with Julia set of a hyperbolic regional map. This is nice because the phase space is very complicated. It's a fractal. As a fractal object. So in this case, you can define the Bezoff space on the Julia set, even if the Julia set has zero Lebesgue measure, but you can define some kind of Sobolev spaces and Bezoff spaces over this fractal, and you can prove the quasi-compactness and statistical properties using this theory. Okay. Okay. So what I would like to any questions? Comments? I cannot see the face of your guys. So, okay. What I would like to give you is some idea how this space is, okay? What kind of, how this space looks like. So to define these spaces of functions, I need just a measure space and a sequence of partitions. The nature of the objects of the sets in this partition doesn't matter. I draw here has intervals, but the geometry doesn't matter. You just have a sequence of partitions, nested sequence of partitions like this, and they have bounded geometry. That means the following. You pick an element of the partition K, and pick element of the next partition. So you can compare the measures of these two guys. This quotient is not very small and is not very close to 1. Okay, so by that I mean bounded geometry. Okay, if you have this, you can define that's the minimal structure that I need to construct these spaces of Bezoff spaces. So one example is the dyadic decomposition of the interval. We pick the full interval, divide by 2 equal parts for 4 equal parts, and so on and so forth. So that's the classical dyadic decomposition. You can pick a square and do the same thing. Okay, divide by 4 and then by 16, and so on and so forth. That's another example. You can pick a polygonal region and make a triangulation and start to make proper subdivisions of these. If you make finer subdivisions of this in a proper way, you satisfy this condition too. And in an analogous way, if you pick like a compact manifold, you can start with a smooth triangulation and do the same thing. So in all these settings, you can construct these spaces. This example is a little more abstract. You have a metric space with a doubling measure. So there is a very powerful result, very simple, just 3 pages, but it's a very useful result by Christ that allows you to construct nice sequence of partitions with bounded geometry that are very similar to dyadic partitions in the interval, for instance. Okay, so in this setting of this is called homogeneous spaces. It's a metric space with a doubling measure, and in these homogeneous spaces you can construct these Bezoff spaces too. Another situation is Julia sets with a hyperbolic rational map. In this case, actually, this is an example of Alfred's regular metric space, and you can define in the same way these Bezoff spaces in this set. So this is a warning in the following sense. Usually, because you all dynamicists, usually when you think in sequence of partitions, you think in sequence of Markov partitions, but it doesn't need to be Markov partitions. It can be in some settings. If you are working with some Markovian map, maybe it's convenient to take the sequence of Markov partitions to build these spaces. But for instance, if you have an interval map that doesn't need to be Markovian, you can pick the dyadic partition, and this is going to work typically. Okay, so you choose what's convenient for you, and most of the time is not a Markov partition. Another example that in this case is a Markov partition, you pick the shift, unilateral shift, and you pick a Gibbs measure for some holder, some Gibbs measure for some continuous function phi. So this satisfies this inequality. Okay, so this sequence, this measure with this shift space, the shift space with this measure, the sequence of cylinders satisfies this condition. You have bounded geometry. Okay. Okay. So now I can define my Banach space or Banach space. And to define the idea of this Banach space is called to build this Banach space is using what's called atomic decomposition. So what you do is the following: you pick an arbitrary function and decompose this function in very basic functions. And these functions that are very basic, very simple, are called atoms. So depending on the class of atoms that you choose, you build a different space. So the kind of atoms that I'm going to use is this so-called Sousa atoms. So you pick an element of your partition and pick a function that is 0 outside this element of the partition and is constant inside this element of partition. And the height, how big is the value of the function inside P, is just depends on the measure of P. This modulus of P represents the measure of P to some power that S minus 1 over P. These are parameters for your definition of your space. And this number is negative actually in our setting. So you have this picture. So the graph is kind of a brick. It's kind of a brick. And the idea is decompose every function has a combinations of these bricks. So if, because S minus 1 over P is negative, when the measure of P is big, this brick is not very high. It's kind of bounded, right? It's a very short brick. So this is like, it's very small, as I told you. So this is like a bar of soap, right? The bar of soap is a very nice to be around bar of soaps these days because of this Den virus, right? And so they are very short, okay? They are very short. And if the measure is small, then the height of this brick is very thin. It's very high and very thin. So this is like a hand sanitizer, okay? Very thin and high. So the idea is to, if I give you a function, to check if this function belongs to this space, I decompose this function in a combination of these basic functions, these bricks, okay? So this green curve is the graph of the function that you wanted to represent. And the bricks represent these atoms, these basic functions. So this is basically building a wall. And the big difference about the atomic decomposition in bases in Banach spaces or in Hilbert spaces is that the representation does not need to be unique. Usually there are many ways to build the same function. There are many ways to build the same wall, okay? So the question that you ask when you build a wall is how much is going to cost. You wanted to minimize the cost of the building of the wall. You want to minimize the number of bricks that you use, right? Another question is who's going to pay for it, but now it's not very fashion anymore to ask this, so let's skip this question. So the idea is the following. You pick your function, you have these parameters, S, P, and Q, and you have your function. You represent this function as a combination, a linear combination. These are complex numbers, and these are the bricks. This AP are the atoms or the bricks, okay? So this is sum of all possible elements in this K partition number K, over all possible Ks, okay? So you can combine these bricks to build your function. So there is a cost to build this function this way. And the cost of this is given by this expression. You pick the coefficients that represent the decomposition and make this calculation here. If this calculation is finite for some representation, then you say that phi belongs to your Bezoff space. Okay, so that is the definition. It's a relatively simple definition. So in your harmonic analysis, you usually use, like, say, Fourier transforms, Fourier series, stuff bases, trigonometric functions to define a space of functions. And here you don't need any of these. You just need this sequence of partitions and the function, the cost function, and that's it. Okay. So that's the space where usually you can prove this quasi-compactness of the transfer operator. Okay.
Just one question,
Yes.
Daniel.
Yes.
So you call it SPQ cost, but there is no S in the cost.
There is, because the shape of the bricks depends on X.
On S, okay. Perfect.
Yeah. So the shape of the bricks, you are right. The cost function does not depend on X, but the shape of the bricks depends on X. Okay.
Oh, okay, perfect.
Okay, so this is a very computational thing. You kind of decompose your function in like pixels, right? Something is usually when you see some image appear in your computer, right? JPG images. You see a very blurred image, and then you see the details. So the details, you have more and more details when you increase K. So that's the idea. Okay. Okay. Okay, so that's the norm. So you have many ways to represent the same function. So you need to take the infimum of all possible classes, and this is the norm. This is the norm of the function in this space. So this is a Banach space. It's a very nice Banach space. You can prove a lot of nice properties about this Banach space. I'm not going to talk about this, but this is the Banach space. This is a Bezoar space. And turns out, so this is like a Tetris game, really. So you pick a function and you want to represent this as these rectangles. So you pick the blue rectangle is the rectangle with the full size of your face space. And then you divide by 2, let's say, and pick the largest rectangle that fits below the graph of the function, and so on, so forth. Okay, so that's the idea behind this atomic decomposition. And what is nice is that these basic functions are very nice, very simple. So you can multiply them, add them in a very simple way. Okay. So turns out that if you have, you can ask you how this
Ask you a question, Daniel.
Yes.
Do you have? There are examples when there are because these Bezoar spaces are bigger than the LP spaces.
No, they're smaller.
Okay,
they're
okay.
smaller. They're smaller. So usually they're compacted, embedded in one LP space. Okay, they're usually smaller because you need something smaller because in these Lebesgue spaces, the Perron-Frobenius operator is not a quasi-compact operator. Okay.
Yeah, it makes sense. It makes sense.
Okay.
So there are examples. There are examples that are one and in the other. It's easy to find.
Examples of?
That are in LP and are not in the Bezoar space.
I don't know if I. So there are examples of functions that belongs to LP. It does not belongs to the Bezoar spaces. Yes. Yes.
Yes.
So these spaces are much smaller actually. So there is a compact embedding on LP. So usually they're much smaller than Lebesgue spaces. There are many functions that are Lebesgue belongs to LP but does not belongs to the Bezoar space.
Yeah. Okay, thank you.
Okay. So what's nice about this, why I'm calling these Bezoar spaces is a very abstract setting, right? Bezoar spaces are usually defining Rn or something. Actually, there is a way to define Bezoar spaces by Han, Lu, Yang for homogeneous spaces that is much more general than Euclidean spaces. And turns out that this definition on the setting of homogeneous spaces coincides with the classical definition. So if you pick like an interval or a square or a cube and make dyadic partitions of these, then the Bezoar space that you get using this method that I described to you is the same that the classical Bezoar space. The same thing with smooth compact manifolds with a volume form, polygonal regions in their Rn, hyperbolic Julia sets. So in these classical settings, this actually coincides with the Bezoar space. Okay? But the description is much simpler, I think. That's what I like about this description. Okay. Okay, I'm not going to talk about this. So there's a long story about, don't have too much time. So it's a long story about atomic decomposition. I'm not going to talk about this today. So just to finish, let me try to explain to you, I'm going to give a very vague idea, but I think it gives you the main idea in this work with Arbieto about the quasi-compactness of how you prove the quasi-compactness in this space. So the idea is the following. The idea is you pick an arbitrary function, you decompose in these bricks. So these bricks are like these rectangles that I show you here. And the positions of these bricks, the graph of these basic functions, should fit these marks in the floor of these floors that are given by the partition that you have, the sequence of partitions that you have, that you see here. So, but you have this domain. So this is a piecewise expanding map. So there's these domains of the branches that is not Markovian in general. So these marcations in the domains of the end and the beginning of the new branch is not related with these markings in the floor. So the idea is forbid these lines. So when you represent a function, you avoid these traced green lines, vertical lines that you see here. This position is, for instance, forbidden. So the idea is the following. You pick some basic function. You wanted to see how to apply the Frobenius operator in this basic function. So first you decompose that function in basic bricks that fits the domains of the branch. So in the beginning, the support of this measure of this function does not fit one of the branches, one of the domains of the branches. So you need to cut in half, cut again, until you fit the domains of the branches. So each one of these rectangles now is inside one of the branches. And then you represent this function in these floors in the appropriate way. So that's the idea. And if you have so this is called dynamical slicing. So if you have, this can be very complicated in more dimensions. For instance, in this case, you have 4 domains for this expanding map, 4 branches for this expanding map that are given by these fractal lines here. And you have the support of one of these basic functions. And he intersects 4 domains. So you need to decompose these in smaller functions with smaller support that fits each one of the branches. So this can be very complicated. And so in general, this is the idea. You pick the function, decompose in bricks that fits the demarcations, and apply the Frobenius operator. When you apply the Frobenius operator, the function is not a brick anymore, something more complicated. You know, the potential can be complicated, can be very complicated. So you have a complicated function. So now you need to slice this again in little rectangles and put back in the this warehouse. Okay, so this is like towers, but it's like a backward tower. I don't know how to explain this. So if you start with a brick, you slice it to fit the demarcations, apply the Frobenius operator, and then represent this again as bricks. So that's the action of the Frobenius operator in this space. So that's the idea. And so basically what you need to do is to understand what your dynamical systems, how your dynamical system acts on just one brick. That's the idea. Okay, so pick one of these bricks, and if you pick a brick in a higher level, you can see he's smaller. Okay, you can see that this is smaller. So this is very high, and this is smaller. So the height of this brick in a higher level is smaller. So when you apply the Frobenius operator, basically what this function does, let's suppose that the potential is constant to simplify, it's lambda, right? So when you apply the Frobenius operator in this atom, what happens is that you just composite this atom with 1 over L, x over lambda, sorry, and multiply by 1 over lambda. So what you can see that this area here and the area here is the same, okay? Thinking the potential has log of the derivative, okay? When you take this potential, it preserves the integral of the atom. So this area is preserved. So, oops, sorry. I don't know what happened. Oops, I mean, going back, I'm sorry. Yeah. So basically, this is what happens. this is what happens. So when you apply the Panford-Benz operator, what you get is just a fraction of the atom of this level. So this atom has a higher area than this one. So that means that one unit of atom goes to a fraction of atom when you apply the Panford-Benz operator. And that explains the contraction. So that's the idea of the contraction. So the action, I'm finishing in a few seconds. So when you apply the Panford-Benz operator for a function, a general function, first you decompose the function in these rectangles. And this is like bad because the representation, well, it's not bad. There is some representation that has pretty much the same norm that the norm of custody that the norm of the function. Then you need to slice these guys to fit the branches. And this is bad because you get a new representation of the function, but it's not so good as the original one. So you lose some control of the norm. Then you apply the Panford-Benz operator. When you do that, you have contraction. So that's the only part that is good. So the blue part is the good one. You have a contraction of the norm of the space in this case. And finally, you put all together. And this can be a little bad too, but it's not so bad. So anyway, the point is that if a typical function, oops, sorry, I don't. Okay, so what happens is the following: if you pick a big atom, just a finite number of big atoms, this bad part is very large. Is very large, and for small atoms, the dynamical slice is not so bad. So that means that this bad part is not so big. So what happens is that you pick a function, an arbitrary function psi in your space, you decompose in the large atoms and the small atoms. The large atoms, there are just a finite number of them. So this is a finite dimensional subspace. In this part, the image of this part can be a very large norm, but you don't care because this is finite dimensional. This is the compact part of the operator, let's say. And for small atoms, there are many of them, but for these ones, this term is not very large. So this can be smaller than one. So you get that this application for psi to L of psi, the small part of psi, is a contraction. So you decompose the action of the Panford-Benz operator in two parts: a compact part, a finite Hank operator actually, and a contraction. And this is exactly the quasi-compactness of the operator. Okay. Okay. Sorry, I'm a little late. Thank you very much for your attention.
Thank you.
Thank you very much, Daniel. So, any questions, comments?
Thank you, Elizabeth.
So I have a couple of questions.
Yes.
Can you hear me? Yeah, so the first one, can you apply these atomic decomposition things to like a hyperbolic setting instead of an expanding type of setting?
So I think you can, but you cannot use the same class of atoms. So it would be a more complicated class of atoms because it should be something that is anisotropic. It has different behaviors in different directions. So I think that would be something similar to standard pairs in for Anosov maps, for instance. You have the atom is just maybe a finite number of leaves, of stable leaves, let's say, and you make combinations of these. So that's a problem because when you use the Panford-Benz operator in Anosov things, you actually apply measures, right? Not in functions. So you need to do atomic deposition in the space of measures or distributions to be said. So I think this is very promising. I think is an exciting way to see these things. But I never try in details to do it. Yeah, but I think it's a very interesting thing to see if you can use atomic deposition for hyperbolic things instead of expanding things. Yes, I believe so. I firmly believe that's possible. Yeah.
And maybe a second question is, what program did you use for making your slides? They're pretty cool.
So I use a Keynote in the Mac. So it's a Apple software. So use a Keynote to do the pictures, and you can use a LaTeX zip to use the equations, draw the equations, this open source LaTeX zip, and transport to this Keynote, the PDFs.
So that Daniel is the only one that can do this with the Keynote. With
you can do in PowerPoint too if you wanted to. I think
PowerPoint
it's the same kind of yeah.
Anyhow, okay.
I propose maybe a mini course in the next event.
About Keynote. Yeah, okay.
I took note already.
I like this a lot. So let me just say that I'm very happy to take part in this commemoration. As Jacqueline said, our graduate programs are very young, 50 years, right? I think ICMC is going to do 50 in the next year, maybe. So it's very, if you are very young, I think I'm very happy how much Federal Universitario has accomplished in some short time. And you're seeing a lot of young people in many areas, in dynamical systems in particular, in Federal University, continue this tradition of do good math, good dynamics, and I'm very happy to take part of this.
Good, thank you. Thanks for the kind word. And well, any more questions or comments?
I could have some questions. Daniel, thanks for a beautiful talk. I heard part of this talk in Lorenzo's seminar, but my internet is not great at home and I'm not allowed to go to my campus. So it keeps breaking, but each time I see these, your talks, they're amazing. So I think you should have a mini course where Daniel can give a 3-hour lecture where we can really appreciate all the slides. Because so many of the animations, I was like, oh, I want to see this. It's amazing.
Thank you.
So my questions were like about, so I think I had 2 questions. Yes. One was, what happens if you don't have an Alphos regular space? So, you were giving this nice example of a hyperbolic rational map, right? Hyperbolic rational map, Julia said. But what if we took something like parabolic or geometrically finite rational map? And if you don't like that, you could think of a Kleinian group, and say that let's look at the limits.
Well, I don't know the details in this kind of thing, but see, homogeneous spaces are more general than Alphos regular spaces, right? So if I have metric space with a doubling measure, this is not Alphos regular metric space. So it turns out that for every, so you can apply this theory for this setting, the setting of homogeneous
doubling.
Yeah, with the doubling measure. Yeah, I didn't try to apply, but I think you can define the space in this setting actually. So actually what people do is the following: you pick a homogeneous space that's a metric space with a doubling measure, and you change the metric to get that this new metric with this old measure is Alphos regular space. So and then you do whatever you wanted to do. So that's the way to define Bezoff spaces for homogeneous spaces. That was these 3 actors. There's a preview papers in the 70s or 80s maybe about Bezoff spaces in homogeneous space. That's the way to do it. You start with homogeneous space, associate that with Alphos regular space, and then apply the theory. I don't know if I answer your question, but
yeah, it's interesting because I think sometimes you can get the space as you are describing, which is not homogeneous doubling. So
You see.
in such a case, sometimes this comes out of parabolic maps, and
Yeah.
The usual way out of it to apply thermodynamic formalism is to use some sort of induction. So, like Lysan-Young towers, something like that. So I was wondering
you're absolutely right. So you can apply this in this setting too. So, for instance, let's take a Kohler-Ekman map, and with a map with a critical point, and you can ask maybe if you have decay exponential decay correlations for Bezov functions.
Yeah.
And I think the way to approach this is using inducing. I mean, or towers, or it's curious that because there are some previous results, for instance, where I cannot remember the name. I can send you the reference if you wanted to, where people study invariant measures for Kohler-Ekman maps using towers, and they prove that the density belongs to the Bezov space. So
I've never seen
this is already no, actually. They didn't use that they used that to study some probabilistic properties. Maybe it's not a very well-known paper, but it's a very interesting paper, and they prove that belongs to the Bezov space, one of the Bezov spaces. So I think you can apply this for situations where it's not so nice, right? So critical points and parabolic points and things like that. Yeah.
Yeah, it would be lovely to, like the class you just mentioned, that was also in my mind, is can you do this for topological Kohler-Ekman,
yes,
to prove
I believe so.
properties.
I think that is a nice, it would be a nice problem to prove this for Kohler-Ekman or topological Kohler-Ekman maps.
Yeah.
I strongly believe that's true, it's true, that you can prove like exponential decay of correlations for Bezov functions in the Kohler-Ekman case, or maybe something with some polynomial decay of correlations for something with some summability condition and so on and so forth. Yeah, but as you said, you need to use some induction. You want to replace the original dynamics for something that is expanding, piecewise expanding, or something like that to be able to use this theory. Yeah.
Right. And this is really interesting. Yeah, it's so yeah, I'll email you, then maybe you can send me.
Okay, I can send you the references. Yeah. Yeah.
And so my other question is very naive. So this Christ paper, you mentioned that
yes.
Christ did this, right? This
not the Christ, the other Christ. Yeah.
Yeah.
And yeah. So yes.
So I was just wondering. So I think in the theorem on your slides, you had compact metric space that was doubling, and then you did this Christ, right? So
yes.
So if you're in that situation, compact metric space doubling, then I believe that the partitions have this property you mentioned called bounded geometry.
Yes,
right?
Exactly.
This is clear.
Yeah, but it's actually more than that. You can. So what's nice about this Chris result is that he gives a very special. It's not every partition that you pick that gives the classical Bezov space. So that's this partition given by Christ gives the classical Bezov space. So there is a partition where the sets are very regular. It's very regular, so you can remind a little bit Markov partitions. So it's a very interesting result, and it has just like 3 pages or something.
Yeah, I wasn't aware of this at all. So this sounds very interesting because
that's very, very interesting actually. Yeah.
But your theory, does it really need so in your slide on bounded geometry, you need it for all K, right?
Yeah.
At every depth.
I can explain to you why we need this bounded geometry. Is that in Bezov spaces there are many different characterizations of the functions. You can define the norm explicitly, or maybe you can use some average oscillation kind of estimation. So there are many different definitions for Bezoar spaces, and all these spaces coincide. That's what's nice about Bezoar. It's one of the things that makes Bezoar spaces nice. If you have this bounded geometry, you are able to prove that all these definitions in this setting coincide too. So this makes things more simpler. But if you don't have this bounded geometry, I suppose some of these definitions is not going to work in this setting. So maybe you get different spaces with different definitions. But I think you can, part of the theory, you can use it. Yeah. But I didn't try, I confess.
Perfect. Thanks a lot for a great talk.
Thank you. Thank you for the questions.
Okay. Good. And so thank you again, Daniel, for this beautiful talk. So let's thank him again, please.
No.
And so, Jacqueline, so.
Well, I guess if everything fine, we give 5 minutes for people refill their water glass. No?
Sure.
And we restart in 5 minutes. I think it's better, no?
Okay.
Is it okay? Is it okay?
Yes, okay, okay.
Well, yes. So if I'll keep you don't need to go out on the Zoom, just maybe turn off your camera. And
Hola, Pepe.
Hola,
¿Cómo estás?
¿qué tal?
Vou
Wellington?
colocar você como
de barba.
co-host.
Sí, sí, grande barba.
Oi, Pepe.
Oi, Zé, tudo bom?
Vamos indo. Já saiu o calendário da vacina para minha idade.
Que legal. Bom, que bom.
O calendário, né? A vacina não.
Zé.
O calendário eu já tenho também. O meu calendário é julho do meio do ano.
Sim.
É legal.
Eu coloquei você como co-host, se você quiser tentar compartilhar.
Ah, tá bom. Deixa eu ver.
Vou buscar um pouco de água já. Tá bom.
Um detalhe. Já. Não tem nada a ver com a qualidade do Keynote.
O keynote é só o Daniel, não se preocupe.
Pô, mas tá bonito, tá bonito. Vou pegar um chazinho.
Chá, Daniel, mas é gelado.
Não, chá quente.
Chá quente. Bom.
Chá mate.
Uhum.
Tá tudo quente hoje.
Não,
aqui aqui também.
Tá quente aí também, né?
É.
Tudo bem, Zezé? Tá com a cara de cansada?
Tá sem som, Zezé.
Estou testando.
Qual é a data da sua vacina?
É março?
Março? Ah, tá bom.
A primeira ou segunda semana de março, não.
Aqui ainda não temos.
Bom, aqui a gente tem calendário, né? Mas se nenhum esperto passar na frente, como acontece, vamos ver.
Mas será que vai ter vacina para março?
Pois é, não sei.
Queria estar um pouquinho mais confiante, mais otimista. Mas...
Pode ser que haja, mas é aquele lance, né? Aquela incerteza, né? A gente não sabe exatamente.
Alexander, when you want to start, I guess the 5 minutes passed already. I don't know.
Okay.
It's up to you.
Okay. Okay, so the next speaker is Jose Vietes, also known as Pepe, from Universidad de la República de Salto. And Pepe is a very good friend from UFRJ and collaborate much with Zezé. And well, it's responsible for the development of the mathematics in Uruguay, especially in the theory of expansive systems. And it's a great pleasure to have here in this conference.
Okay.
And he will talk about the Lyapunov exponents, expansiveness, and entropy for set-valued maps. Thank you, Pepe.
Okay, thank you very much. It's a pleasure for me to be here celebrating the 50th anniversary of the Programa de Posgraduação en Matemática da UEM, da UFRJ. Oh, fortunately this has to occur in just by the web method, not in to be there, which we would like, of course. Okay, let me try to present a bit the things that I have to speak. First, I will give you the definition that we adopt in respect to the set-valued maps. First of all sets that we will consider should be closed subsets. So we have two spaces, X and Y, and which are Hausdorff, and we assume that for every point x of x, we have a non-empty closed subset f of x of y is given. In this case, we say that f is a set-valued map. It's not very difficult to understand why. From x to y, and write f x with this strange, well, just a dash with a small circle in the point. That means that f is a set-valued map, a multi-map, if you wish to use that. And we reserve the phi x, the arrow to y, when we are referring to a single valued map. And we will usually use capital F, and I will not say it every time. So if it is necessary, I will say capital F, but usually I will say F. Okay, this is the definition, just very simple. And the idea is that the subset f of x is just a closed subset, not not every kind of subset, but just closed. Okay.
Pepe, sorry. Pepe,
yes.
Try to put your screen, the full screen. You know that because it's appears something in the. You know
I
how.
see. I will try. Let me see. A ver,
You go, you go to ver.
Yes.
Yes.
In the menu upwards. Ver.
À esquerda.
The menu à esquerda.
Sim, no topo do arquivo, adicione, ver.
Yes, ver. Yes.
Isso.
Exactly.
Modo pantalla completa.
Exactly. That's okay?
Perfecto.
Thank you.
Okay, thank you.
Okay, so that's just the definition of set-valued map, and this is just a remark. A set-valued map can be defined as a closed subset of the Cartesian product x by I in the following condition. For every x, f of x is different from the empty set. It's not void. Well, so where they appear set-valued maps, set-valued appear in what are called in control system theory multi-valued functions. In this context, usually in control system theory, what they try to understand is what kind of control should be applied to govern the system. It's not exactly what we are trying to study here. So they are thinking on something that evolves with the time. Oh, that is said, it's here, no? At a given time, t naught, and we want to know what occurs at a given time t, for instance, with the famous coronavirus. Of mathematical economics, there are also several applications that are more or less related with that kind of control. Where the multi-valued functions are sometimes called correspondence in this. And Pierre Aubin was one of who was studied this kind of in the context, this kind of multivalued functions, set valued functions in the context of mathematical economics. Well, you can also think in a differential equation where there is no uniqueness of solutions. So we have to try to understand the evolution of all the solutions when you lose uniqueness. In a certain sense, that's the question. And also, if you have a non-invertible onto map, the inverse relation, we can think, you can think it as a function, a classical function from x to the 2 to the power x, given by f minus 1. That way, for every x, that f minus 1 of y is the subset of x, of all the x, such that f of x is y, gives up, of course, a particular example of set valued map. For instance, you can pick the expanding map in the interval 0, 1, x corresponds to 2x modulus 1, 2 times x modulus 1. So you have 2 pre-image, and from that you can pick other 2 pre-image and so on. And one natural source of this kind of set valued function is you can think of a diffeomorphism and you simulate the dynamics given by such a diffeomorphism. A point usually is known only approximately. Instead of knowing x, you know x plus epsilon, and that adds some error to x. And if you try to simulate this in the computer devices, this x plus epsilon is changed by the floating point representation of this, and so add a lot of errors. So the idea is, since you know only f of x in a fuzzy way, it may be natural to replace it by a set capital F. Now I have to say capital F of x, leading to a set valued map. Perhaps this capital F may take all into account all possible trajectories, or perhaps only that's with more plausible that you have a big probability to have them. Okay. What we want to address here is first, we wish to address define or accept a definition. There are previous definitions of expansive set valued maps. Investigate if there are Lyapunov stable points for set valued map defined on a compact manifold. And in this case, perhaps you have to also define what is the meaning of Lyapunov stable point, and prove that under this definition that we picked, prove that topological entropy is positive under some hypothesis. Define Lyapunov exponents for set valued maps in a similar way that it can be done for homeomorphism when you do not have differentiability, and relate entropy of set valued map with positiveness of Lyapunov exponents, and that's all. So let's try to attack all of these points. First of all, we will give some basic definition. They are more or less standard, but I do not assume that people is acquainted with with this kind of set-valued functions. So, in fact, the composition of those set-valued functions, g and f, is just the union of g of y for every y belonging to f of x. And if you have y for in the capital Y set, the set f minus 1 of y is the set of x such that y belongs to f of x, to capital F of x. And from this definition, we may define the iteration of the set valued function just using this kind of definition. Okay. And then, okay, so if you rest just with this kind of function, such a generality is very difficult to prove anything. So we impose some kind of regularity in this kind of functions. And so here is what is very well known after semi-continuity. If for every closed set C of Y, the set f minus 1 of C is a closed subset of X. See that what is saying upper here, f minus 1 of Y is not such that X is such that Y is in f of, is not only Y belonging to f of X. Okay, I'm not expressing me well. Because there are two kinds of f minus 1. One is not named the larger counter image of f, and the shorter one counter image of f, and we are adopting the larger one, which can be represented in this way for when you are speaking about single points. The idea is that you substitute y for instead of y, you consider a subset of y, a subset of capital Y, say L. Then what you are considering is all that X that such that f of X intersects the L, the subset L. But in this case, it's the same as saying to Y belongs to f of X. And the short quantity image is in the case when you consider the case when f short counter image of Y is of not of Y, but of a subset L of capital Y, is such that f of X is totally included in L, not intersecting L. So one is in the case of single valued function, both concepts coincide. But here is not, and that's so we adapt, not to bother you about with this kind of consideration, we adopt just this one, which corresponds to the large counter image of Y. So we say that f set valued function is upper semi-continuous if for every closed set f minus 1 of C is closed on X, and is lower semi-continuous if for every open set the set f minus 1 of U is open in X. And if if both, it occurs that f is at the same time lower and upper semi-continuous, we say that it is continuous, of course. And f is Hausdorff continuous if given epsilon, there is a delta such that if the distance between the points x and y, oh, I should use another typography because y appears that they are in the subset y, but in the set capital Y, but this is not the case here. Then the Hausdorff distance between capital F of x and capital F of y is less than epsilon. So the distance is the usual Hausdorff distance between compact subsets. But in this case, when you are working with compact sets, is really a distance. Okay, if you consider the following proposition said that in fact the both definition to be continuous just f capital F lower and upper semi-continuous and saying that f is Hausdorff continuous is the same. So let M be a compact metric space and f a set valued map. F is Hausdorff continuous if and only if is continuous. Well, this is the finish of the basic facts about set valued maps that we will use, apart from the different definition that we will use from now on. So define expansive set valued maps, we introduce the following definition. The F suborbit of X, an F suborbit of X is a set of the form, yes, is the sequence X sub J such that X naught is equal to the original X and X J plus 1 belongs to F of XJ. And this is valid for positive and negative J because we have defined it in what is the meaning of F minus 1. Okay. So what is the meaning of an expansive multivalued map? Richard Williams proposed the following definition, and we shall denote it by RW expansiveness. I put Richard Williams because there is you know that there is Robert Williams, very famous, and in order not to confuse both, I have put here Richard Williams. So F of, since we are thinking on the action of a set valued map, we will consider F a set valued map from X, so from capital X to capital X. And we say that it is RW expansive, we say with an expansive constant delta, if whenever X and Y are different, each F suborbit, we have defined they here, okay? Each F suborbit of A, say A, of X and B of Y, there are some instant N, let's say N, such that Xn belongs to A and Yn belongs to B, and the distance between this image by the set valued function of X and Y is apart more than delta. And according with this definition, you see that every pair of distinct F suborbits have to separate at certain time n. And of course, if this initial distance from x to y is less than delta, then you have to have that f of x cannot intersect f of y, and or f minus 1 of x cannot intersect f minus 1 of y, because if not, you lose this property. You can consider, if you have a point of intersection, say C, for fx of intersecting fy, and w for f minus 1x intersecting f minus 1y, then you consider these suborbits x, y, and then x goes to, for the future, to C, and to the past for to w, and the same for the other one, and you cannot have expansiveness. So one of them have to not to intersect, and that means that you have a sort of local injectivity of f or of f minus 1. That gives a certain, it's rather strong, I think, that this kind of definition, because you have to separate every pair of suborbits. One idea is to try to mild this condition and say, well, not separate the suborbits, but just to separate in the Hausdorff distance a certain iterate of f of x on y. Say you have a constant alpha such that the Hausdorff distance between fn of x and fn of y is greater than alpha for some n belonging to the integers. This is another way. This is perhaps it's not very good for some things, and it's better the other one. But I think that this seems more plausible in certain conditions. Of course, if you accept this kind of condition, you have to have some proposition about what occurs when you iterate, because you have that f of x is a closed or compact if you are considering in a compact manifold or a compact set M, everything, and you consider what occurs when you iterate for the future. There is some kind of compactness or closedness, and that is true. The following propositions say that this is really true. It said C of M in the family of compact subset of M, and F, a set valued map, continuous in the sense of Hausdorff continuity, or the lower and upper continuity are both the same, with F of X belonging to C of M. And then if K belongs to C of M, if you are considering this just a subset of C of M, then F of K also belongs to C of M. If you have the property that the property holds for points, then it holds for compact subsets. Okay, using this, you have the definition of Hausdorff of expansiveness. Excuse me, given above is okay. Well, let's give some examples. Well, these are really simple. You can see that is define f of c from M. I have put it here in the closed interval 0, 1 because and let's define f of c equal to multiplied by c modulus 1. and 2 multiplied by c plus a half modulus 1, then you will have this kind of behavior, and f is both expansive in the sense that we have defined here, and also is expansive in the sense that Richard Williams has defined. I have to say that Richard Williams called mappings to this kind of set-valued maps. Okay, and recall that there are no expansive single-valued maps. It's more or less known that this for homeomorphism, but it is also true for single-valued maps. In fact, Richard Williams gave an example give the proof of that there are no expansive single-valued maps on 0, 1. Then the other one is just a bit artificial, you can say, because we have substituted the interval 0, 1 with this 2c modulus 1. We have substituted by the square of c and the square minus c square, joining with another point 0, and you can think that all of that is in the plane. Okay, and then you can see that f is expansive in the Hausdorff distance, but f is not RW expansive because you have added this point, and you will have sequences. Of course, you can pick point C and C prime very close one to the other, and then when you consider f of c, they will be really very close. All of the images, they have no time to separate, but you have added the 0, and so when you add that point 0, you lose because every point is okay. It cannot have this kind of injectivity that I have speaking a sort of local injectivity of f or of f minus 1. Okay. Of course, there are also no expansive homeomorphisms on M, which is just a circle plus a point. And then you can also build an example on the torus. Then you can prove that this example built in this way, in the first coordinate you multiply, this is more or less the same as before, and in the second coordinate you divide, but it's more or less the same kind of example as before. And here is the proof. I will not bore you with this kind of proofs. And there is we Artigue and Cese and me have exhibit a diffeomorphism F in the torus B, or bitorus, perhaps I have to say bitorus, don't know, which is too expansive, but not one expansive, which is the same as to be expansive. That is the meaning of too expansive, that you have. Okay, you say that f is n expansive if and only if for all x the subset of points that shadow the orbit of x at a distance less than epsilon is bounded by a certain name n, capital N. And in this case, we are thinking on two expansions, so there are only 2 points. Then, instead of thinking about a diffeomorphism F in the torus with two expansive, we can think that it as an expansive multi-valued map, just considering the union of the image. And this is true. The idea is the following. You have 2 points, X and Y, and if they rest, first of all, they are only 2 points. You cannot have a third point shadowing X or Y, because if that occurs, then one of them have 3 points. So they are only, perhaps there is no point shadowing the orbit of X at a distance less than epsilon, but if there is one, it is only one more. And the attracted A is an attractor, the capital A is an attractor here. Let me see where is the capital A is an attractor and capital R is a repeller. And so F restricted to A and F restricted to R are hyperbolic, so they are expansive. So the only way that you will have points that are at a distance less than a certain distance and they rest is that they are wandering. You cannot have non-wandering points in that condition, because if you have 1 point, for instance, in the attractor and the other one in the repeller, so they are far apart, of course. You have one in the attractor and the other one is not in the attractor, so iterating to the path they separate. And the same if you have in the repeller. So the only way that you will have 2 points is here is that you have points that both are wandering. So if you pick another point, the point that shadow another point C is the point that shadows on the orbit of C also have to separate from that of X and Y, because if not, you lose two expansiveness there. So that is the idea why this capital F is a set valued expansive. And there are points as close as you wish, X and Y, that should shadow, because if not, they will, because the construction of this example is gluing two torus with one of them an anosov, say, and the other one the same anosov, but glued with F-1, and you have to use, how do you say that, a polar transformation in this annulus where they have to glue. And this, in this way, one of the, say, the stable manifold of this will be the straight lines, the red straight line, and the other one, say the unstable manifold, will be, of that point, will be the blue circles. And you can consider as small as you wish the intersection of the distance between the two intersections when you have two, between the red lines and the blue ones. And that's the reason why the dynamics is too expansive, not only expansive. And also the way why we have to, we can use to define the set valued map. Also, there is also another kind, perhaps the most interesting. You can consider an expansive homeomorphism with an expansive constant alpha, and you know that if you just consider homeomorphism, when you can perturb it, even restricting yourself to homeomorphism, not going out the homeomorphism, just to the continuous function, you will have in that case that there is, you lose expansiveness. There is no, it's not an open property. But there is something that an open property here, that is this, that if you have perturbed f, there is a neighborhood of f in the CNOT topology, so that the G is a homeomorphism belonging to that neighborhood. And for a pair of points, we have that the distance of Gn of x, Gn of y is less than alpha, then automatically it's less than alpha over 2. If there are points that rest at a distance less than alpha, they have to rest at a distance less than alpha over 2. So you cannot have points at 3/4 of alpha or something like this, or they the orbits separate more than alpha, or they are at a distance less than alpha over 2. That is used for Lebowitz to consider the quotient space. You identify points that the orbits are less at a distance less than alpha, so they are at a distance less than alpha over 2. And if you consider this, you have a relation between points x and y are related if they are at a distance less than alpha, and you have 3 points. So if you have a point that the orbit rests at a distance less than alpha, x with y, and then y with z rest at a distance less than alpha 2, so they rest at a distance less than alpha over 2, and so by the triangle inequality, you will have that the orbit of x and y, x and z, are at a distance less than alpha, and then they are at a distance less than alpha over 2. So this enables to define a equivalence relation between points. And instead of doing, and then you can consider the quotient space with this equivalent relation. It will be a metric space. It will be, but the topology of the space should be rather complicated. The only case that it is not rather complicated is when you have that f at the beginning is topologically stable. In that case, the quotient space is the same as the original manifold. If not, it will be a complicated metric space. Okay, but instead of perturbing and considering just the quotient space, you can consider the multi-valued, the set-valued map f of g, defined by just the union of the orbit of g of y belonging to a of x, where a of x is just the union of all the points that their orbits rest at a distance less than alpha. You will have that f of g is an expansive set-valued map. Also, it is continuous, but perhaps, and so you can use as you have not perturbed the manifold, perhaps it's a good idea to try to explore this path, going not perturbing and preserving the properties of nice manifolds, and not going to a compact metric space that perhaps is rather difficult to study. In fact, Cerminara and Martin Sambarino have studied this, have proved that they have a metric, good metric, because Lebovic just said that it has a good metric and so on, but he proved a little about this. Say, and just you can use that. Okay. So these are the just examples. And so let's go to the one of the points that I would like to talk about is just given a compact metric space and a continuous set valued map, we wish to define the epsilon stable set of X. And this is defined in this way. We consider an Fx, an F sequence such that it starts with x naught equal X, and we define the epsilon stable of X as the set of F of capital F sequence Yn such that there exists an F sequence Xn which goes such that the distance between Xn and Yn is less than epsilon for all n positive. The stable set, of course, is the same as the same kind of definition, replacing positive n by negative n. And we will say that X is a Lyapunov stable point for a set valued map if there is, for some epsilon, there is a delta such that if Y belongs to the ball of center X and radius delta, then the F sequence Fyn, all of them belong to the stable manifold, stable set, because you have no manifold at all here. The stable set of X with respect to capital F. And then we have proved the following. Have to remark that there are no Lyapunov stable points for an expansive homeomorphism on compact manifold. And there are no positively expansive homeomorphisms defined on compact manifolds of positive dimension. Of course, with zero dimension, just single points, and there are, if you have compactness, you can have some kind of expansive homeomorphism. But if you consider positive dimension, here we are speaking about the Hurewicz dimension of the manifold. So we say the theorem is the following: if M is a compact manifold and F is a set value continuous RW expansive map, not the other kind of expansiveness. We cannot, perhaps it's true, but we cannot prove it for the other kind of expansiveness where we have Hausdorff separation of Fn of X and Fn of Y. Perhaps it's true also. What I'm saying here for RW expansive, then the set of Lyapunov stable points of F is empty, o sea, there are no Lyapunov stable points, or it coincides with the whole of M. It's an alternative, it's one or the other, and it's rather strong. And surprising for me, at least at the beginning, I think that there was no, but in fact they are at hand. you can consider this example, f of S1 to S1, just dividing the angle f. You represent S1, the points of S1 as raised to the y multiplied by phi power, and then you consider just a raised to I phi divided by 2 and I phi divided by 2 plus p, and this is, of course, all points of this will be Lyapunov stables, but the inverse of f minus 1, will have a expansion. And so you will have a positive expansive homeomorphism, a negative, but you can reverse everything, and you will have a negative expansive homeomorphism. You can reverse the time, and you will consider f minus 1 as a new g, and so consider positive g. And this is the same. This is exactly, this is an expansive multivalued map where all the points are Lyapunov stable. Expansive for the past, but it is expansive. RW expansive. Okay. Then let me see. What can I say? It's more or less 5 o'clock. What is the time that I have? Is there any time?
I think that since we started late, it's because perhaps 10 minutes.
Okay. So here we consider also expansive multivariable map. Recall we have defined below after we have defined that f is a suborbit of x if it's the sequence of the form given here. X naught is equal to x, and x j plus 1 belongs to f j x of j for each j in the integers. So that we can define the orbit of f as the set of all the suborbits of f, and orbit of f of x as the set of all the suborbits of f such that x naught is equal to x. And then given a suborbit xk, we denote by O sub n of x as the suborbit from 0, from k equals 0 to k equal n minus 1, just the first segment of suborbit. And it's we say I have written here. Okay, I think that's okay. Because we are speaking of f of capital F of x g minus 1, and here is g, and if you put g minus 1, then you obtain 0 to n minus 1. And then we say that a subset of that suborbits is n epsilon separated if for any segment of suborbits the distance xy ey is greater than epsilon for at least one y in between 1 and n. And let denote Sn of epsilon the greatest cardinality of an n epsilon separated set. It's just the similar definition. We are going to define the topological entropy in the similar way that it's done for single valued maps. It's the Bowen's definition, in fact, but applied to this context. Then we define topological entropy as for set value using the Sn of epsilon by the limb when epsilon goes down to 0 of lim sup of 1 over n of log of Sn epsilon. Here the usual definition, and then we can have various alternatives to try to prove things about topological entropy. For instance, we can consider continuous set-valued maps that f of x is compact and connected. So it's a continuum for every x of m. And then we consider that if gamma is a continuum, also contained in M, then f of gamma is compact and connected too. So that it's also a continuum. I don't know why I have used compact and connected, and then I have used continuum, but it's what I have read. Then if M is a piano space, recall that a piano space is just a set that is compact, connected, and locally connected, and F is a expansive set-valued map such that f of x is compact and connected for all x, then the topological entropy of f is greater than 0. And the proof of theorem used the fact that there is an analogous proof given by Cordeiro and Pacifico, so I will not say much more about this. Then you can also try to prove to avoid the problem of the problem is not a problem, it's just a property that you have claimed to have a compact and connected image of points. But sometimes you have not this kind of property. So you can say that you recall that a space is called sequentially compact if every sequence of the space admits a convergent subsequence. The proof of the following result can be found, for instance, in this book of Jossi's book, Introduction to General Topology. Assume that you have a sequence of sequentially compact metric space, then the countable product of this space is also sequentially compact. And this is used for us as we get that if M this is a compact metric space and we consider countable family of sequence, there is a convergent subsequence of them. And this is used where? To prove that in the case of RW expansiveness, we have uniform expansiveness. Recall that that means that if the original points are at a distance greater than, say, a delta, then in order to obtain that the distance of the subsequence is greater than alpha, at a certain instant n, then you have to wait for some n not too large, between minus capital N and capital N. That is the idea. And to prove this lemma, we use this sequentially compact lemma. Okay, I will don't bother about this. And then you can prove using that the entropy of RW expansive is positive for RW. The topological entropy is positive for RW expansive set valued maps. Here we do not consider we do not have to accept the hypothesis that the image f of x is connected. Okay. Then after that we define. Okay, we don't define because this is very well known in the context of set valued maps. invariant measures for set valued maps. There is a difference to this. If you consider a single valued function, then the measure mu is f invariant if mu of f minus 1 of b is equal to mu of b for all the Borelian subsets b of m. And the definition for set valued maps is that mu of b is not equal mu of f minus 1 of b, is less or equal mu of f minus 1 of b. That is the definition that works for the case of set valued maps. And in the book of just known set valued analysis by Pierre Robin and Hélène Frankowska, it is proved the following exactly. That in our context we do have that there are invariant probability measures U for F. And then we can define a lot of stuff that you see the points, the subsets compact that are not equal to K, this B star of K delta N, the subsets A that are compact but are not equal to K, and such that distance of Hausdorff of Fg of K, Fg of A is less on equal delta. And the same for the negative N, this is for positive N, and then you can define capital H of delta as the supremum of all the sets A that are contained in B star of K of delta N, such that the Hausdorff distance of Fn of K, Fn of A divided by the distance of Hausdorff distance between K and A. This is, and also you can define that for the past. No, in this case, not for the past, but with the infimum of this distance. And this allows us to define more or less Lyapunov exponents about using that. But you have to take care of that because the distance can go to infinity, this quotient, very quickly. Why? Because I give an example that is upper semi-continuous in the following page. But here, we require also that it is a sort of Lipschitz continuity. So in order to control the distance between the things, we require that there is some K greater or equal than 1. In fact, that F of capital K, F of capital A is less or equal K distance of Hausdorff capital A, capital K, capital A. And the same for that, for the F minus 1. And then using the equation 1, yes, we define for positive N the lim sup of 1 over N of the log of H delta of Xn, and using equation do the same for the other kind, lambda minus of delta. And we can prove the following theorem. This is not very difficult, that for X mu almost everywhere, the limits, this kind of limits exist and are finite, and capital F invariant, and and using that this decreases and the other one increases when delta goes to 0, we can define the maximal and minimal Lyapunov exponent for f at x. And then we can prove the following. Again, something about the topological entropy. If we have a compact manifold and f of m, or a set valued map, such that there is a non-trivial continuum gamma contained in M with capital of, with the Lyapunov, the greater Lyapunov exponent of x positive for all x in that continuum, then the topological entropy of F is positive. It's not very difficult to prove that. So let me show that there is no, it's, cannot have, for instance, just upper semi-continuity is not enough, because you can consider, for instance, F in a pseudo-anoso with a singularity P, and the function that you are considering, f of x, is just to the point x, you consider f, capital F of x is the union, is the unstable epsilon, the local epsilon unstable manifold of f of f of x, and then we can see that you approach this, the epsilon unstable manifold of x approach this, but the distance, the Hausdorff distance between the unstable manifold of P and the unstable manifold of x do not go to 0, because there is this other prong which rests at a distance greater than, for instance, epsilon over 2 for every x that you consider here. So even if you consider a point in the stable manifold of P, it will approach more and more and more the point P, but the unstable, and this prong converge in the C1 topology even to this pair of this unstable manifold, to this pair of prong, but there is one that is not considered, so the distance continue to be, the Hausdorff distance continue to be greater than epsilon over 2. Okay, so let's finish with this. I will speak about selections. Perhaps we can consider this in the future if the pandemic allows us. Given a capital F from M to M, a set valued function, and F from M to M, a single valued one, we say that F is a selection of capital F if for every x we have of f of x belongs to capital F of x. So one problem is that sometimes you do not have selection, but perhaps you have approximate selections in a certain sense, and you want that this selection want to be continuous or at least measurable, something like this. There are some results given by, for instance, by Michael's selection theorem about this. And what we are going, what are the questions that I would like to pose is that given F expansive, does it exist given capital F a set valued expansive? That exists F continuous or at least measurable, such that the topological entropy of capital F is equal to that of the, I don't remember, how you say when of F with when it is not capital.
Small f.
Small f.
Small f. Okay. Small f equal to topological entropy of capital F. Okay. The same question can be posed with respect to the Lyapunov exponents. Can we find a small f such that the of course, which is at the same time a selection, not anything, which is a selection that can we find a f, small f of m to m, such that the Lyapunov, at least the greatest Lyapunov exponent of f is equal, the small f is equal to the greatest Lyapunov exponent of capital F. These are the two questions that perhaps we can, or someone which are not us, can answer us in the future. Okay, that's all. Thank you very much for support. Okay, many thanks.
Okay. Thank you very much, Pepe.
Okay.
For the talk. And we pass of time, but perhaps we can take one short question or comment.
I would like to ask you, Wellington, here. When you work with that expansive dynamical systems, we are always limited by the dimension of the space, because by Mayer we have expansive homomorphisms must be defined in a
of course
finite.
But these set valued functions are not homeomorphies.
Yeah, I know.
They are just maps.
Yeah.
So in fact, we have presented cases where there are set valued maps, for instance, in the unit interval, and there is no expansive homeomorphism, and there are set valued maps. Of course, at the beginning, I was confused about that also. I was okay.
No, yes.
If X is finite dimensional with positive dimension, then 2 to the power of X is infinite dimensional. And so, why can we speak about expansiveness in that context? Because it's not the same context as the case of homeomorphisms. That's the question, I think.
Yeah, my question would be that for set valued, it's always the same. It's also the same. If you can have set valued in infinite dimension, or you have the same limitation.
Okay.
For almost.
I have not think about that. Perhaps yes. I don't know the answer now.
Okay.
Okay.
But okay, good. Well, so thank you very much, Pepe. And let's thank Pepe again, please.
Thank you.
Thank you very much.
And also the other speakers that talked today. Was very nice.
Yeah.
Thank
you. And Jacqueline, perhaps you want to talk some anything?
So, well, we'll come back tomorrow morning, 11 Brazilian time. We'll be back tomorrow. We have more 2 days. Well, I can say that we decided to do this conference in 3 days, the first time, because Rio is a quite expensive city. So we thought that if we invite for a week, the speakers to arrive on the weekend will not be able to afford this. So we kept 3 days, but now it doesn't make much sense because The speaks are quite cheap these times. So thank you for accepting this circumstance.
Okay.
But it's just a silly comment so we can finish the day in a more fun way. So see you all tomorrow.
Okay.
See you.
Ciao.
Bye.
Ciao.
Bye.
Bye-bye. See
Bye
you tomorrow.
bye. Thanks.
Bye.
Thanks a lot.
Alexander, tá ainda por aí?
Oi, eu tô.
Ah, tá. Então deixa eu... Fica um instantinho para eu falar com você.
Claro.
Deixa eu parar aqui.